So that said, I'll introduce our speaker. So today we have Burcu Can, who's at the University of Stirling, one of my colleagues, and Burcu got her PhD at the University of York in 2011 and has worked as a lecturer for a while since then at Hacettepe University in Turkey and in Wolverhampton, the UK, before coming to Stirling. And her expertise is in natural language processing, which is obviously of a great deal of interest across the community at the moment. So I won't say any more. I'll hand over to Burcu and let her talk. There should be a bit of time for questions at the end. Burcu, would you like to kick off?
Yeah, thanks a lot for coming to this talk. So this talk is actually more like a roadmap from large language models to small language models. And I will give you an overview of the language model landscape, starting from the gigantic, powerful large language models, and that we will see that these models, they are gradually shrinking over the time in the last couple of years. So that's why the small language models, they have become more popular nowadays. And you will see a lot of elephants in my slides because I will analogize LLMs with elephants with the large language models, because elephants, they can consume a lot of plants. I don't know if you have any idea, but an adult elephant can consume, for example, around 300 kilos of plants every day. And these models, they are very hungry of resources, any kind of resources as well. So that's why I try to analogize the LLMs with the elephants. And they have both good memories as well. So that's also another thing. So this is the structure of my talk. First of all, I will talk about large language models and their limitations, their success levels. And in the second part, I will mainly talk about the prominent small language models, the prominent techniques which are used in the small language models. And I finally mention a little bit about our recent study of a baby language model, which is much more smaller than a small language model. So first of all, what are these large language models? So I'm sure you are all familiar with large language models. So they are deep neural networks with billions of parameters and even trillions of parameters these days. For example, I think still, if it is, Wuda, I think, sits at the top with this 1.75 trillions of parameters. So they are trained on massive text corpora like GPT-4, 5, 5.2, Gemini, etc. And this is one of the recent works by Jones and Bergin in 2025. So they had this experiment. So every participant, they were given 5 minutes to have a dialogue with a machine, with a model, or with a human. So if they can correctly identify, it means that they passed the Turing test. So I'm sure you are all familiar with Turing test as well. So interesting thing is that GPT, I think GPT 4.5, it was misidentified over 70% of the time. So it means that they have some human behavior, maybe some human intelligence as well. So they can pursue the dialogue as a human. So they are really good at it. I'm sure we are all using them for any kind of reasons these days. So you can see how this scaling over the time actually has been done. For example, we started with the Elmo around 94 million parameters, and it was around 100 million parameters at that time, like 2018. But only in few years' time, like 2021, we see that billions of parameters were used in the recent large language models. So it means that these models, they have increased in scale by an order of 5,000 times. So this is a lot. So still they are increasing more and more. So if we look at the landscape, large language model landscape in 2024, we will see lots of large language models, and we see lots of smaller language models as well. So this is in time. So we can see the number of the parameters based on the timeline, and the bigger the circles are, the bigger the models are in terms of the number of the parameters. And the circular ones, the circle shapes, they are owned by the companies. They are usually not open access, and the diamond shaped ones are open access. So most of them, as you see, they are not open access. They are owned by the companies. And then we can see, for example, this is the landscape in 2025. We can see the major LLMs here, and this is based on their successes, based on this multitask language understanding. So this is not only evaluating their language capabilities, but if they can also generalize it to diverse domains. So this is the ideal level you could see, and this is the human expert level. So all of these large language models, they actually perform over the ideal level, and even some of them, for example, GPT-o1, it performs over the human expert level. So they are good, but actually, what are we sacrificing for these success levels? First of all, the compute requirements. So these models, they require lots of compute power. For example, tens of thousands of GPU or TPU clusters we need to train them. And in terms of the data requirements, they need trillions of tokens to be trained. And also they have a very high cost. For example, the estimate for GPT-3, it was around $4 to $5 million, the overall cost, but this is only GPT-3. So they don't disclose the costs, but we guess that it is over hundreds of millions of dollars they cost. So in addition to these resource requirements, what are the limitations? What are the risks? So these models, they have a very terrible carbon footprint, as you may be already aware of. For example, this study from 2019, and they measure the carbon footprints of a round-trip flight, for example, from New York to San Francisco. It is around 2,000 pounds of carbons emitted. For a human life, it is 11,000. For an American life, I hope there are no Americans around here. So it is 3 times more than the normal human life, in terms of the carbon emissions. And a US car, including fuel, in their average one lifetime, it is 126K pounds. And if you look at the transformer, which is a small model, it is not like billions of parameters or trillions of parameters. It is only 200 million parameters, and it is 5 or 6 times more than the US car carbon emission overall over a lifetime. So this is only for training only once. So as you say, this is a lot. Or in terms of the energy consumption, so if you look at the annual energy consumption of GPT 3.5, this is not for training, but using it, testing, inference of it. So it is 44,000 megawatts. But if you look at the household, only one household, for the average annual energy consumption, it is 10,000 kilowatt. So it means that it is equivalent to energy consumption of only the inference time of the GPT 3.5 is equivalent to 4,000 households energy consumption. So this is a lot. So as you see, the higher the number of the parameters are, actually the higher the energy consumption is. So this is one of the things. Or reliability. We all know that they are open to hallucinations. Maybe they are better than before, but still they hallucinate. We already know that. There are lots of court cases. For example, Air Canada, it lost the court case after one of its customers used the chatbot, which was available on their website, and the chatbot gave some false information, and the Air Canada made an argument that it is not responsible of the chatbot, but actually this was rejected by the court, and the court said that Air Canada is responsible of all the information which is available on the website in addition to the chatbot. So they had to pay for all the expenses of the customer. And the misinformation, we already know that we cannot rely on all the information which is generated by the large language models. For example, two US lawyers, they used GPT, one of the GPT versions, to generate court briefs. And in these court briefs, there were some false citations to non-existing precedent court cases, and they were fined for $5,000, and they had to also send an apology letter to the judges whose names were incorrectly used in these court briefs. Another thing is the reliability bias. So these models, they use all possible available data on the internet. So this data has lots of stereotypes, bias, harmful language, and so on. And so, which means when you train your model with this data, you have all these biases in your model existing as well at the end of training. So for example, this study from 2021, Abid et al., they find out that the Muslim is analogized to violence over 20% of the time, and Jewish is analogized to money 5% of the time. So as you see, the biases exist in the models. And another thing is the privacy and data concerns. So they don't care about the copyrighted work. And all these models, the OpenAI, Microsoft, Google, etc., so they use all the possible available data on the internet, whether they are copyrighted or not. So I think this was in 2023. The Times sued OpenAI and Microsoft because of using their copyrighted work. Still, as far as I know, this is an ongoing case, and it hasn't been resolved yet, because this will be an example for the others. And I know that the AR regulations are going on, but this is not only a commercial issue, it is also political as well, because there are lots of AI lobbying going on. And Silicon Valley, for example, they have invested recently over $100 million to oppose the AI regulations. So it is also political as well. And here the Times said that they can use this on copyrighted work because it is under fair use. So in American law, fair use means you can use any kind of copyrighted work for educational or for research purposes, but this is not research purpose or educational purpose. So this hasn't been resolved yet. And another thing, the representation of the languages in the large language models. For example, if we look at GPT-3, it only contains 7% non-English text and the rest is English. So if we look at the solutions by language, for example, you will see most of the NLP solutions are developed for English. Whereas if you look at the population-wise, actually English is the minority. And if you look at the low resource languages, it makes up majority of the population. So the yellow color here on the right, you will see. So we have over 7,000 languages around the world, but most of the data which is used to train these models, they are on English actually. So it means that they will work a lot better compared to the low resource languages. So in summary, they are very good, they are very successful, powerful, they can do anything, and they can even flirt a little bit. I actually came across this Reddit post as well. So, but they come with their potential harms and limitations. So they have lots of problems with honesty and responsibility. So this was the first part of my talk. So in the second part, we will look at the small language models. So what are small language models? Why do we need them? I will give some examples to the small language models, and then we will look at baby language models. So what are small language models? Actually, there is not a clear line between small and large language models, but in my talk, actually, I would classify the small language models having parameters less than like 10 billions of parameters. So it will be a couple of billions of parameters. So it will not be millions of it will not be trillions of parameters or hundreds of billions of parameters. So it will be a couple of billions of parameters. So they will need lower compute cost. They are faster. They can be deployed offline. So if for example, companies usually they have privacy concerns, and these models, they can be deployed offline, so you don't need to use cloud-based large language models. And usually they are tailored for specific tasks. So large language models, normally they are general, so you would expect them to perform any kind of task or to be able to reply to any kind of domain-specific task. But whereas here, we are not aiming to have a model which is capable of answering any kind of domain-specific language, but only one specific task we would like the model to perform. So they are more accessible. So which means you don't need to have lots of resources in terms of the compute power, in terms of the data, if you would like to fine-tune it, and so on. So if you look at the general architectural or general features of the small language models with a comparison to the large language models, you will see that in terms of the parameters, they have like millions or to few billions of parameters, and they are trained on much smaller and often specialized data sets, and they are faster in inference. They can be deployed on device, and they can be deployed on cloud as well, but usually or always the large language models, they are cloud based. And so why small language models? Actually, we have seen these signals like couple of years ago. I think this was in 2023. So one of the articles in The Economist, the article was about the bigger is better approach to AI is running out of road. So we have seen this signals for science from a couple of years ago already. So the models got bigger and bigger, but now they are shrinking over time. And there is another article from MIT Technology Review. You will see in this article they are talking about this MOLMO, which was developed by Allen Institute. And they discovered that this model, even though it has like 70 billions of parameters, it performs much better compared to a model, I think GPT, one of the GPT models, which has trillions of parameters. So it doesn't mean that always the bigger is better. And we see the timeline here. For example, up to 2023, the models got bigger and bigger, but in 2023, actually, we see a big trend of smaller models. For example, the Gemma 2 billion was introduced, Phi 3 by Microsoft Research, or GPT-4 Mini, or Gemini, for example, 1.5, Ministra. So we see lots of smaller language models from 2023 onwards. So if we look at this family of SLMs, small language models, we see lots of them now. For example, Llama has different versions, like 8 billion parameter version, or Microsoft Phi 3, it has like 3.7, 8 billion up to 7 billion parameters, Gemma, Mixtral, OpenELM, or Qwen, for example, it is specialized on coding. So this is also another small language model. For example, compared to BERT, the still BERT is 60% smaller compared to the BERT. Tiny Llama, for example, it has only 1.1 billion parameters. Mobile BERT, for example, it is optimized for mobile usage, and so on. So what makes small language models so attractive? Because they are accessible, they are affordable, which means we can use them for research purposes as well. So they are more accessible for academia. So you don't need to you don't need to uh, you don't need to be in a company to be able to use these models, but they are more accessible for anyone. They are cheaper to develop and easier to customize. For example, you can easily fine-tune these models as well on a maybe even a single GPU, and they are more energy efficient as well. And you would guess also the carbon emissions would be much more lower. So let's have a look at some prominent examples. For example, one of them is Google Geometry, and which was developed by Google DeepMind. So it has different versions from 27 billion up to 1 billion parameters. I wouldn't consider 27 billion and 12 billion parameter ones as small language models, but 4 billion and 1 billion ones, they are smaller models that you can easily run on a single GPU, and their embeddings, their number of layers or hidden dimensions, they are much more smaller compared to a large language model. So what are the techniques used in, for example, in Google Geometry? They use 5-to-1 interleaved attention. So what does it mean? Normally, in a normal transformer architecture, in a large language model, normally we have global attentions in every layer, in every decoder or encoder layer. So which means for the context length, you need to calculate the attentions between every possible word pair. Whereas in 5-to-1, we have four, for example, local attentions. So we don't look at all the context window, but we look at local windows. But after every 4 layers, only the global attention is calculated only after 4 layers. So it means that we don't calculate the global attentions in every layer, but every 5 of the layers we calculate the global attention. So it makes the things faster. It can be easily and faster, quickly trained. And what they use is also grouped query attention. So in the vanilla attention, normally in the very first transformer architecture, so this is the multi-head attention, which was used in the very first large language models. So for every query head, normally we have one key head and one value. So this was the beginning point. But later on, it was discovered that if we group the queries and if we have sets of queries, for example, here, for every set of query, we could have only one key head, which means we will have only key metrics. And for every couple of them, we will have one key metrics and one value, which means we will have less parameters. And less parameters means more efficient training. Or you would have, for example, for every query, for all the queries, you would have only one key head, one value head as well. But here grouped query attention was used. Mistral 7 billion. So it is also another transformer model, and this one is also using this grouped query attention. And in addition to that, they use sliding window attention. So in the sliding window attention, they don't use the global attention. So in the global attention, normally between every possible word pair, we calculate the attention. So we have a huge attention matrix. Whereas here in the sliding window attention, we choose a local window. For example, in this case, it is just 3 words. And only for these 3 words, the local attentions between every possible word pair is calculated. So it means that it will have a lower cost. It will be trained much faster because you will not have a huge attention matrix at the end, and you will have much more smaller attention matrices. And they also use byte fallback BP tokenizer, so they don't have any unknown token. For example, in the previous large language models, if the token is not found in the training data, unknown token is assigned. But whereas here they use the byte encodings of the words, which means every word will have a byte and they will not have any unknown token at all. So MetaLlama 2. So in the MetaLlama 2, it has different versions as well, like 7 billion, 13 billion, 70 billion. The 70 billion, 13 billion ones, maybe they are not small language models, but they all use similar training strategy. And in this one, so they use ghost attention. So what does it mean? So it is not a replacement for the original attention mechanism, but whereas here, so If you are, for example, using a large language model, maybe you will notice after uh, first of all you give some instructions, but after a very long round of dialogue, you will see that it would lose the instructions which was given at the beginning. So it just forgets all these instructions which are given at the beginning. Here, in order to avoid this forgetting, so they use this ghost attention. So how does it work? So they have this language model which has been trained on the data. So this is the pre-training stage. Then they train a rewarding mechanism, which is another neural network model, and this like a reinforcement learning. So this reinforcement learning mechanism, it learns how to rank the outputs. So for example, for one prompt, you will have many replies, but they are ranked by the reward model. And once they are ranked by the reward model, these selected ones which have higher scores, they are used again to fine tune the model. So you will see the fine tuning stage here. So with this ghost attention mechanism, so this is called ghost attention, so they have more refined outputs, and it doesn't forget about the instructions which are given at the very beginning of the dialogue. So architectural details in the small language models, normally they are much smaller compared to the large language models. The number of the layers, for example, it ranges from 6 to 12, the hidden sizes up to maybe 1000, or attention has 4 to 8, and the parameter counts are usually 1 billion to 7 billion. They are usually distilled, so which means you have a bigger model, and from this bigger model, usually it is called like a teacher model, and from this teacher model, the student model is trained to mimic the outputs of the teacher model. So they are much smaller in terms of the parameter sizes and in terms of the architecture as well. And they use more efficient attention mechanisms as well. For example, they use this local windows. They have more sparse attention mechanisms like the one in the long former, or for example, in the lean former, it is another attention mechanism. The bigger attention matrix, it is projected into a smaller attention matrix. Our performer, for example, they change the order of the calculations in the QKV, query, key, and value matrices, and so on. So there are lots of different efficient attention mechanisms used in the small language models. And they have much more smaller vocabularies, which ranges from, for example, 16 to 50K. And lots of on-device optimizations are also done for the small language models because we expect them to work in, for example, even the mobile devices, etc. So now I will touch a little bit on prominent techniques in small language models. For example, quantization. So most of the recent models, they actually use this quantization. So every weight is represented as a floating point normally, and normally floating 32-bit is used. But if we reduce the precision of the weights, for example, from 32-bit to 16-bit, it means we will have a much smaller model, and the weights will be much smaller as well. So it will use also lower memory, because imagine you have lots of matrix calculations, and the intermediate calculations, they need to be stored somewhere, but normally they cannot be stored on the GPU, because GPUs normally they don't have a very big RAM, etc. So these kinds of problems we would have with high precision numbers. Whereas with the low precision, normally they are much more smaller and faster to train. And this is one of the floating points. It was introduced by the Google Brain Float. Although it is 16 bits, the range is the same as the floating 32 bits. So as you see here. And most of the recent models, if you are using some of the large language or small language models from the Hugging Face, you will see that this GPTQ at the end of the model, so which means that they are quantized. So pruning, so in the pruning, we just simplify the model by removing some of the parts from the model. For example, we have the full model like that. We have the layer normalization, attention, etc. So we estimate the importance of all the embedding layers or the heads or the neurons, etc. So once you estimate the importance, we rank them and we prune some of them, which does not contribute to the overall loss. So there are different mechanisms, that there are different approaches here as well. For example, you can look at the loss. So if some of the embeddings or some of the heads or the layers, for example, if they don't contribute to the loss, you can just prune them. Or you can look at the activations. For example, if there is not much activation going on in some of the heads, you can decide to prune them as well. So there are some approaches here to decide how to prune them. So efficient training, I think this is one of the most important features of the small language models. They don't use all the available data on the internet. They use actually small high quality data sets, and they do lots of pre-processing on these data sets. For example, they do lots of deduplication, because imagine you are training your model on the same samples again and again, which means you are actually losing some of the training on the same examples. So this deduplication actually makes the training more efficient, because you have the data and which is quite distinct. All the samples, they are distinct from each other. And also curriculum learning is used a lot. For example, in the curriculum learning, instead of training the model in one stage, you just start from the simple data set first, and then you gradually train it further on the complicated, on more complex data set. So this is one of the studies from 2023. And they find out that, for example, this is the orange one, and it is trained on unprocessed data. And whereas in the light blue one, for example, you see this is trained on the code textbook. So this is for a coding model. And it is trained on the code textbook, which is organized very well, structured very well. So as you see, there is a lot of gain between the unprocessed and the processed data. And this is not fine-tuned at all. For example, once you fine-tune it, you can see the dark blue ones. It shows the fine-tuned performance. So this actually, this is one of the backbones in the small language models, the dataset quality. And the knowledge distillation, so this is used a lot in the small language models. So once you train a teacher model, which is a quite big model, then you can use these soft labels, the outputs. So either it could be the soft labels or the probabilities, the logits from the teacher model. Then you can use this to train the student model. So the student model actually tries to mimic these soft labels or the probability distributions. So it makes some soft predictions. And at the end, you can use this model to do your hard predictions. So this is much smaller model. And for example, in Orca 2, which has been developed by Microsoft. So in that one, they use a technique which is called explanation tuning. And explanation tuning, so a large language model is given to Orca 2. And instead of mimicking the final outputs, actually the whole reasoning process has been also given to the Orca 2. So it just mimics the reasoning as well, in addition to the final outputs. So this is a distilled version of the much larger model. So parameter sharing is also used a lot. So normally in every transformer layer, we have different sets of parameters. Whereas, for example, you can, in Albert, for example, a light BERT, so all the layers, they use the same sets of parameters. So in this case, you will have less number of parameters to train. So this is also another techniques used. And one of the other one is mixture of experts. So this has been mainly used by Mixtral. And in this one, instead of having a dense network means you will use all possible subnetworks in the in the complete neural network architecture. Whereas in the mixture of experts, you will divide the whole network into subnetworks, and you will have a router, and the router will decide to use which experts to compute the final output. So this is like a gating mechanism. So in the Mixral, it was like 64 experts, and they don't use all the experts, but only two of them are used. For example, here you have this feed-forward neural network. So this is the dense model. So in the dense model, you use all possible subnetworks. So you use all the feed-forward neural networks. Whereas here in the sparse model, you will use only some of the feed-forward neural networks. For example, out of 64, you will use only two of them to compute the final output. So in terms of the size of the model, it may be bigger, but in terms of the inference and the testing, it will be much faster because you will not be using the whole neural network architecture. So it will be better in terms of the latency. So in summary, the small language models, they provide cheaper solutions, they are more affordable, and the gap in terms of the performance, it is not big anymore. If you look at the recent small language model benchmarks, and the quality of the data sets, in addition to all the architectural tweaks, I think the most important thing is the quality of the data sets. So there is a wide range of publicly available high quality data sets that you can use to train small language models. I haven't put them on my presentation, but there is a wide range of open access small data sets which are very high quality. So even smaller language models, so baby language models, they have smaller than 1 billion parameters, and you can run on a GPU or even on a CPU. Normally, they are used as fine-tuned because at the beginning they only have some language capabilities, but not like a general word knowledge, and they are usually distilled from larger parents, for example, distilled GPT-2, etc. And for example, Tiny Llama, Mini LM. So here the idea is that, so as humans, we are exposed to less than 100 million tokens when we come to age of 12 years old. Whereas the smallest possible language model has, for example, 3 billion parameters, 3 billion, sorry, tokens used in the training data. Whereas the largest one, for example, Llama 2, only for the up to 2023, 2 trillion tokens were used to train the Llama 2. So which means actually the BERT has a language experience equivalent to 300 human years, and whereas the largest one, which is equivalent to 20,000 human years. So the gap is big. So as humans, actually, we are efficient language learners. So I accept that. I'm not a believer of Chomsky, but I don't know if you believe in or not, still the gap is too big. So we can see some examples to baby language models. For example, baby Berta, it has only 8 million parameters, 30 million words in training, or baby llama, for example, it has only 10 million words trained. So this is one of the challenges, like baby language model challenge, which was introduced in 2023. So I think the fourth one will be organized this year. So the idea is that given small amount of data, so small means 10 million up to 100 million tokens, can you train a model to learn some basic knowledge? In addition to that, can we learn some language capabilities and so on? So this is like a challenge, like a competition. And lots of different strategies have been used. For example, curriculum learning, distillation models, lots of linguistic biases. For example, as humans, we have some linguistic biases, and according to the language acquisition theories, so can we use these linguistic biases in the training? of these baby language models. They changed the training objectives. They did lots of modifications in the architecture and so on. So if we see the performance of these models, you will see, so these are the different models, the competitors in the challenge. And here the dashed line is the Llama 2 skyline and the human score is the line. So this is the blimp score. It is more like a grammatical evaluation. So how fluent, for example, the model will be in generating that language. Or glue score, it is more like a fine-tuning score. So it is more like pragmatics or little bit discourse, maybe some basic reasoning or language understanding and so on. So as you see, we are not far, actually these models, they are not far from the Llama to Skyline, as you see. So it is just below 80%, but this is just, for example, the highest one, the highest performing one, it is just below 80%. So if we look at the last year's baby challenge scores, we will see that so still it falls short of the human skyline or most of the models, but they are not far from the Llama 70 billion skyline. So even though they have just millions of parameters, a couple of millions of parameters, they perform actually not on par, still fall short, but still not very far from the Llama 70 billion skyline. And even, for example, in this case, this is the 100 million tokens. This is for 10 million tokens. So as you see here, they can actually slightly outperform the Llama 70 billion skyline. So they are actually excellent at basic chat, grammar, text embeddings. So they can even do some common sense as well, and even do some single step reasoning, but they are weaker at, for example, ambiguous tasks, or if you have more complex reasoning, like chain of thought kind of tasks, they are not still very good. But maybe that's what you need. If you are doing a simple classification, maybe you will not need a large language model or even a small language model. You will not need it. So baby language model, maybe that's what you will need for your task. So this is one of the recent models that we developed, and it was published in last year's baby language model. And these are my collaborators. The first one was my PhD student. Now she is a postdoc, and one of the colleague from Lancaster University. So here we actually use some theories from child language acquisition. So in most of the models, they use this BPE tokenizer, byte pair encoding tokenizer. Whereas from the child language acquisition, we observe that, for example, children, they can only build the vocabulary at the very early learning, at the very early stages of the language acquisition. So here, instead of using this BPE tokenizer, we use the morpheme-based tokenizer. For example, instead of splitting them with the BPE, we either splitted them with just a rule-based morphological tokenizer or using a morphesser, which is an unsupervised morphological segmentation model. So once we tokenize them with this morpheme-based tokenization, we use curriculum learning. And in the curriculum learning, instead of training the model to learn syntax or morphology, we just aimed to train the model on the vocabulary building stage, which is the same as the child language acquisition. So in the second stage, we introduced the morphemes gradually, and then we expected the model to learn the morphological structure as well. So at the end, we have these results. For example, we use two different architectures, GPT-2 and GPT-BERT. So if you remember, for example, GPT is a decoder-only model and BERT is an encoder-only model. So in the GPT-BERT architecture, this is one of the architectures which was which was one of the participants actually in the baby language model challenge. So they use both of them at the same time. So it is like a weighting mechanism. Sometimes it uses it uses both of the objectives from the encoder and decoder training strategies. So in this one, we actually obtained 72%. For example, the blimp. Blimp is more like a grammatical capability of the model, and it outperforms actually the baby language model baseline from the previous year. And for example, this one is quite interesting. This is word knowledge. This is word knowledge evaluation, and it actually substantially outperforms the other baseline models with a substantial margin actually. And also the entity tracking as well. So entity tracking is more like for example, if you have the pronouns in a sentence, you would track which, for example, words it refers to this pronoun. So just tracking this kinds of pronouns, kinds of task. So findings, morphological information definitely helps in learning language, and different training strategies, they actually lead to different results in different architectures. For example, in the GPT-2 architecture, we don't have similar results compared to the GPT-BERT architecture. So this is one of the interesting findings. So in different architectures, we should use different training approaches. And curriculum learning, it definitely improves the results slightly when used with the GPT-BERT architecture. So this is another finding we have come up with. So in conclusion, I think the future is small and mighty. So the bigger is better philosophy is coming to an end, which I think. And I think we need more efficient and less data hungry, less energy consuming models, not only for the environment, but to make the models more accessible as well for research wise. And small language models, they are not general models usually, and we don't expect them to know everything, but maybe that's what you need. That's what you need for your task. So you don't need to use a very general large language model, but maybe a more specific but smaller language model that you can train or use privately. Maybe that's what you need. So we need to actually consider all the possibilities that we would have. I think the landscape is getting bigger and bigger. So we have lots of options now. So it is not that we are bound to use large language models anymore. So we have lots of options actually from the small language model landscape, even the baby language model landscape as well. Yeah, I think this is the end of my talk. If there are any questions, I think we will have 10 minutes to discuss.